Okay, so let's talk about this problem here, which is in section 5.4, problem number 1. It's talk about population growth, but I do want to point out that we are not going to use the formulation I introduced in class because there's a minor difference. As you can tell, it tells you, it's asking you what's your annual growth rate, what's your annual percentage changes. So here's what's actually going on. If you can recall the interest problem where we had compound interest, you remember we had two sets of formulations. The first one is some kind of like what's your initial interest, and then you have e to the power of n times t, where the n is how far it grows, it's compound interest grows continuously. Versus the other formulation for the interest, it's compounded, let's say, annually or monthly or something like that, right? So it does not change continuous. What exactly does it mean? It means you don't get your interest every single teeny tiny one over a millionth of a second and things like that. You have your principal for, say, let's say $1,000. You hold it for a year. At the last day of the year, they compound the interest for you and only change once. And if you interest were compounded monthly, so it's at the end of the first month, it compounded interest. So if you started with $1,000, at the end of the first month, you have $1,000 plus the interest it generated at the end of the first month. And then together, you have slightly over $1,000 as your principal now, and you compound your interest throughout the second month and so on and so forth. So your interest, the money you have, grows only 12 times throughout the year. So this one has the formulation of 1 plus, right? 1 plus how much you increase per unit cycle, which could have been which the formulation is something like R over N, right? And then it is N times T. And this N could be 12 if you compound monthly. This N could have been 1 if you compound yearly. This N could be 365 if you compound your interest 365 times. So when I talk about the population growth, which the formulation looks a lot like the second one, we are talking about the continuously change of population, which makes sense if you want to talk about the population on Earth. You change the population all the time, right? It's continuously growing. It doesn't make too much sense for you to say my population only grow at the end of the first year, at the end of the second year. Nothing changes throughout the year. But okay, here's the big but. For this problem in particular, they were trying to make it extremely simple. They are making this assumption, my population only change, okay? It's change once a year. It's change annually. So we're not going to use the population change model. We're going to just mimic the behavior of the compound interest. So you could have said, okay, the money I have in high doubled after 15 years. What's the interest rate I have grow per year? Okay, that's an equivalent way to understand the question. So you want to be a little bit careful which one to use if I talk about annual growth rate. Or do I simply talk about growth rate without telling you what's the specific time length? If I only say the growth rate is, then you go with the exponential growth model. If I say my growth rate per year is this, my growth rate per month is this, you want to treat it as if it were compounded interest and then use the modification of the first model. So let's go ahead and discuss my problem here. I have my initial population, whatever that is, multiply by 1 plus, how much do I grow per year? Well, my grow annual percentage is going to be R%, right? Percent is that R%. And how many years do I have to wait? I have to wait 15 years in order to generate doubling of my population. Therefore, my problem is 1 plus R%, 15 is 2. So how do I solve this? This is a problem where I want to look for the base. So in order to make my calculation easy, I can try to change the structure so it doesn't look like a problem where I exponential structure, which is relatively hard to solve. So if you have exponential structure, I can change it by moving the exponent in the front because I can take a log. So it's 15 times ln of 1 plus r%, which is the same as ln of 2. So natural log of 1 plus r% is ln of 2 over 15. So what are you looking for? You're looking for the input of a log structure. Therefore, 1 plus r% is, you're going to raise it to e to the power of log 2 over 15. So what's my r%? My r% is e to the ln 2 over 15 minus 1. Be a little bit careful. Percent, okay, percentage is divided by 100, so this r is e to the ln 2 over 15 minus 1 times multiplied by 100, okay? This is what you end up with. And what exactly, when we were asked that what's the annual growth rate factor? So it basically asks you what is the growth you have per year. Okay, this is per 15 years. So what's the growth is like per year? The growth is P0 times 1 plus r%. This is what you have as a growth per year. So compared to the original structure, so when they ask you what exactly is B is this number. Therefore, because you know r% is that, so your B is 1 plus e to the ln 2 over 15 minus 1, which is e to the ln 2 over 15. It's just a matter of the definition. If you don't feel comfortable, you may simply go ahead and ignore the second half of it because the definition is not something we went over in class, not super intuitive. But the first half of it, and when to choose the right model to study the change of population, you want to be a little bit careful about that.